Martina Bremer with Polycore Software. This video shows how to connect a sample multi-core application across two DSP devices using SRIO for communications. Doing this takes about 15 minutes using Polyplatform and MCAPI communications. The development environment is Eclipse-based Code Composer Studio from Texas Instruments, with Polyplatform plugins, and the operating system used is DSP BIOS, also from TI. The hardware platform is a TI evaluation board, which contains a C6678 multi-core DSP with 8 cores. In the Code Composer Studio workspace is a project that contains a RITC configuration and linker command files used to set up the DSP BIOS environment. The workspace includes a Polyplatform memory map, as well as a configuration for Polyplatform resource pools, a basic main C program routine, a C file containing a function stub, RITC platform configurations, and lastly, a target specification for the debugging. The main file contains initialization to the inter-processor communication of the task creation and starting of DSP BIOS. The same main file is used for both cores. Function stubs are used to create the communication between the two cores. The memory map contains constants to be used for SRIO addressing and memory regions to be used for Polyplatform resource pools. We have also created two RITC projects, one for each node, which simply contain one source folder each. The configuration, linker command, and demo main files are the same for both node projects, N0 and N1, and are therefore linked into the projects. The demo main C file is selected in the source folder of the resource projects and dropped onto the N0 source folder. Check the link option and then repeat the same procedure for N1. Select the function stub from the source folder in the resources project and drop it into the N0 source folder. This time, choose to copy the file instead because the function stubs will be modified differently from N0 and N1. We repeat this process for N1. The RITC configuration and linker command files will also be the same for both nodes. Therefore, those files should be linked into N0 and then to N1. The preparations for the demo are complete, and we can work on the multi-core aspects, including defining which parts of the demo will be running on which core. The next step is to create a topology project. A topology project contains topology maps and memory maps, which are used to specify and configure the underlying communications topology. Each topology project can contain many topology maps and one active topology map at any given time. We start by creating a CCS project called Topologies, and then adding what we refer to as a topology nature. The topology nature can be toggled on and off by selecting properties and clicking the Add Remove Polycore Topology Nature option. When the topology nature is added to a project, a directory structure containing memory maps, topology maps, and code generation directories are created. Next, we will add node natures, first to node 0 and then to node 1. We do this by toggling the node nature on and off, selecting properties, and clicking the Add Remove Polycore Node Nature option. With the node nature, we can associate a node project with a topology project and also specify which node of the active topology a node is associated with. We'll create a topology map, called a polymap. We do that by using the New Project drop-down menu, selecting Other, and then selecting Polymap under the Polycore Software tab. Select the polymap folder, then the topology map folder within the topologies project. And we will name it PM2Node. In the Topology Wizard, we select a small profile, which provides a set of predefined values such as number of nodes, max payload size, number of processor to be used in the topology, etc. This allows for a quick start. The values can be changed later. When the project tab contains topology-wide information, including processor specifics such as processor family, type, byte order, and number of cores. The next step is to select the processor. We select the TI C66XX DSP, which has 8 cores and little endian byte order. Then link the memory map into the topology by selecting the predefined memory map from the resources project. Next, we'll configure the nodes, a collection of one or more functions and links representing the data paths. We start in the Topology tab, where we have the 2 nodes on the canvas. We separate the nodes and select the Properties view, so we can review and configure the properties. For the nodes, we want to use DSP BIOS as the OS, and we click on each of the nodes and select DSP BIOS. We add a link between the cores by clicking on the link icon on one node and dragging it into the other. For the link, we want to use SRIO as a transport, and we'll do that by selecting TI-SRIO link driver in the link driver drop-down menu. We only have to add values to the link configuration parameters that are labeled value required. And for this link, it will be the SRIO addresses. More specifically, we have to add the in and out values for one of the SRIO address components for both sides of the link. The values are picked from the SRIO constant values, predefined with easy-to-understand names in the memory map we previously linked to the topology. The memory map is accessed by clicking the Mem button. Once we have finished picking the values, we apply the change, and the link configuration is done. Now we'll go to the Tree tab to configure the pools. We use the memory ranges predefined in the memory map, similarly to the way that we use the memory maps for the SRIO link. We're selecting a section, a range, and then the start value for the range representing the starting address of the memory range, specifying where in the memory the pool will be located. The ranges have been sized to accommodate the pool sizes and cache alignment. We go through them one by one, starting with the combined pool, then message queue pools, and lastly the waiter pool. The sizes of the pools are automatically calculated and validated against the sizes of the chosen memory map ranges. Pools are used to store resources used by the communications infrastructure. The pools offer a wide range of configurability in order to accommodate different target platforms and memory architectures. There is a general set of characteristics that can be configured for all pools. These include, but are not limited to, the location as well as the type of allocation of the pool, in addition to alignment and cache management. There are also characteristics specific to each type of pool, such as the amount of resources and the structure of those resources. We are now finished with the topology configuration, and the only thing remaining for the topology project is to select the active topology. This is done by selecting the topology under the Properties and Polycore Topology. In this case, we only have one topology. When selected, the topology is validated, and then the topology definition for each node is generated. The topology definition contains the configuration specifics. Next, we have to check that each of the node projects refer to the topology project, and also specify which node in the topology that each node project belongs to. This is done by selecting Properties and Polycore Topology for each of the node projects. The properties of each node will determine the proper settings of symbols, file paths, and libraries required for the builder, relieving the user from keeping track of this. When the nodes are selected, the topology is validated, generated, and the node definitions updated. The builder distributes the files to the proper workspace projects. Then we go into each of the node projects and start adding the code to the function stubs to implement the communication between the two nodes. The first thing that we want to do is to add hardware initialization, node initialization, and discovery to each node. The initialization includes a separate module and a template for invoking the module from within the application. Hardware initialization is used to configure and initialize the hardware accelerators. In this example, the queue manager and the SRIO device. Using the template relieves the user from having to do the hardware configuration in the application. The node initialization and discovery is used to initialize MCAPI communication for each node based on the processor, the software environment, and the operating system, and to perform a basic discovery of the node available in the topology. The first step is to generate the initialization modules from core templates provided by PolyTemplates, and then to add the code that invokes these modules from our function stubs. To add the node initialization module, we select it from the drop-down menu and request it to be inserted in the N0 project, and then we do the same for the hardware initialization module. We repeat this for the N1 project. Hardware needs to be initialized first for the function stub in N0. We start with adding invocation of the hardware initialization module. We click in the function at the location we want to insert the code and select the coding template for invoking the hardware initialization. We select the variable, and when we click Finish, the code is inserted into the application. Next, we add node initialization using the coding template. The node initialization module initializes MCAPI, creates local endpoints, and goes through a basic discovery process to find out which other nodes are available in the topology. We're ready to start insertion of the application code for the communication. We create a loop in which messages will be sent and received. We add a send message function using the templates tool. We'll select a blocking send, and then we can see which ports are available on the local node. And if we select the remote node, we can see the available ports on the remote node. Next, we get a template with a selection of different variables that we can choose from. New variable or existing variables of the right type can be selected. In this case, we have message buffer, message priority, status code in number and text formats. When the template entry is completed and the Finish button is clicked, the function code is generated and inserted into the application where we specified for it to be. Endpoints are symbolically defined, which means that they can be moved in the topology without having to change the application. Then we insert a receive function to receive data back from the other node. Likewise, we select a blocking receive function and we go through the same procedure to select the desired variable and complete the template to generate and insert the code. We also need to set the initial value of the data. The predefined topology, topology-aware polytemplates, and the validated templates speed up the programming effort and reduce coding errors. Lastly, we insert a print statement to see our results after we have received the data from N1. As you can see, the application on N0 will send messages and then wait to receive messages back with a blocking receive. In this example, we only touch on the initialization and message function templates. There are templates available for all of the MCAPI functions. The Node 1 initialization code, hardware, and node are identical to Node 0, so we'll take a shortcut and copy the code from Node 0 into the function stub. Messages will go back and forth between the two nodes, so we insert a loop here as well, and proceed to add the messaging functions. For Node 1, we do it in the reverse order, with receiving first and sending thereafter. We insert the message receive and we use a blocking version, selecting the proper port and variables, filling out the template. In this example, we are using blocking send and receive message functions. In this simple demo, there is no other work to be performed waiting for the next message. Blocking functions can also be used for synchronization purposes, whereas in other cases there is work to be performed while waiting for data, in which case non-blocking functions may be preferred. There are also packet and scalar channels available in MCAPI, providing connected unidirectional channels for buffered and scalar communication. Next, we insert the message send function to send data back to Node 0, again using the template. Lastly, we set the value received to be incremented before it's sent back, so we can see the result back on Node 0. As you can see, coding using the template is pretty quick. We rarely do any MCAPI programming without using polytemplates. Let's do a quick recap of what we have done so far. We started by copying and linking configuration files, the demo main C and function stubs into the node projects. Then we created a topology project and topology map with largely predefined default values. We selected the TI-C66XX DSP and configured the nodes using DSP BIOS, links for SRIO transports, and pools using a predefined memory map. The application coding is now completed, and the next step is to build the application. We'll pause the video during the build. The build has now successfully completed for both nodes, as we can see, and it's time to switch to the debug perspective and get the application loaded onto the evaluation board using the TI-XDS100V1 USB emulator. From the debug perspective, we select the EVM C6678 debug configuration. This configuration is set up for 2 cores and they are grouped under Group 1. The other cores are hidden in this view. The board will be initialized and the code will start loading on Core 0 and Core 1. The code is loaded in separate areas of the DDR memory, per the setup in the RITC target platform for each of the cores. It's time to find out if the application runs, and the results are as expected. We select Group 1 and press the Run button. As you can see, initialization and discovery include endpoint creation and discovery of remote endpoints, and is followed by the message printouts. The flow that we set up was to send a message from node 0 to node 1, where it was incremented and then sent back to node 0. From the printout on node 0, we can see that the behavior is as expected. We're stopping the demo again by selecting Group 1 and pausing the execution. Creating the communication between the two cores over SRIO took us only about 15 minutes, not counting the setup of the initial configuration files or the build. The abstraction between the application and underlying multicore platform, provided by Poly Platform, enable a rapid development time. For more information on Poly Platform, please visit www.polycoresoftware.com or just give us a call.